Right, guys? What is the probability of drawing a card that is an ace or a king? Would mean we're doing the probability of A or K. So if I'm using that addition rule, what I would do is take the probability of A plus the probability of K minus the probability of A and K. That's what the addition rule tells us. You guys, what is the probability of getting an ace? 4 out of 52, because there's 52 cards in a deck. What is the probability of getting a king? 4 out of 52. Minus. You guys, what's the probability of A and K? A card that is an ace and a king? 0. Yes? What does that say about ace and king?
Mutually exclusive.
They are mutually exclusive. Perfect. Great, Ella. Hence, the probability of both of them occurring is 0. So we say at 8 out of 52. You guys, what my expectation of what you need to show is the fraction and the decimal. Okay? So it should be about 0.158. Man. Okay, what is the probability of drawing a card that is an ace or a heart? So that'd be the probability of A or H. What's the probability of A? 4 out of 52. What's the probability of getting a heart? 13 out of 52. Minus, are there any cards that are both an ace and a heart?
Wait, 1.
1, so we're going to subtract 1 out of 52. So my final answer would be 16 out of 52, which is about 0.308. Maybe? Someone double check me, 308? One more example. Thoughts on this one? I'm sorry? There's 19 females? I don't know about you guys, but this one, it's hard for me to navigate it, yeah? Like, I know cards, so it's pretty easy for me to navigate cards. But when it's this kind of real-world context, it feels a little bit more iffy to navigate, yeah? So, this is when I might choose to build a two-way table to help me navigate what's what. Like I said, the two-way table is a tool to help us figure out probabilities. All right, so 20 cyclists. So that will be where would I put that? Total cyclists. 13 of which are male. What does that say about the females? 7. 30 runners. 18 are males. What does that say about the females? How many total males do we have? 31. Females, 19. Hey, look, everything adds to 50. We know we set up our table correctly. So now I say, what is the probability that someone is a cyclist or female? We can do the probability of C plus the probability of F minus the probability of C and F. Anytime it's an or, that's what we do. So now using our table, you guys, what's the probability that the person I select is a cyclist? 20 cyclists out of 50. Female? 19 out of 50. Cyclist and female? 7 out of 50. $32 out of 50, which is 0.64. You guys, what is the complement to cyclist or female?
Runners and
Male runners. It's anybody who's not a cyclist and not a female would, in this particular case, would be only male runners. How are we feeling, okay? All right, so I am done. Certainly we should take a little bit of a break. If you haven't filled out that survey, please do so. If you would like to wait until I've graded Kendall's tests so I can pass them back to you guys, no problem. And then that way you guys will be in a place where, you know, stuff. All right, so let's kind of look through this first example. And then you might want to have your test back and look at your test before you fill out that survey. I get that. Okay. Because there might be things on your tests that inform. Okay, how about now? It's not playing or anything.
because you're recording.
I know, but I thought I hit record before and it started playing too. You know, recording and talking over stuff. No. All right, so let's go ahead and look at this. So the biggest idea is if we're talking about multiple events occurring, what we end up doing is multiplying probabilities. Okay, so during the segment on Nightline, it was reported that there is you guys, there's no way it's a 605 success rate. I'm certain that is a 60%, and that is, I didn't hit shift, and the percent is you guys get what I'm saying there? And I just didn't catch it? Cool. There's a 60% success rate for those trying to quit smoking through hypnosis. Find the probability that 8 randomly selected smokers who underwent hypnosis all successfully stopped smoking. Everybody good? Yeah. Okay, so here's what we do. We randomly select a smoker. What is the probability that they... 60%. And so the probability, the probability that the second person quit smoking is going to be, well, that would mean that the first person times the probability of the second person. So this is the first guy. This is the second guy. This is the third guy. Are you guys getting what I'm saying here? And so essentially what are we doing? We're multiplying by 0.6 lots of times. Like a total of 8 times. And if you wanted to write that as 0.6 to the 8th power to make your life a little bit easier, totally fine with that. So again, and or typically still exist in a one event thing. What is the probability that this one event is one thing or another, or one thing and another? It's still one event that you're talking about. Okay? If we're talking about multiple events, we typically multiply our probabilities to get there. Okay? Hey, is somebody who's smarter than me, can you guys help me figure this out? So that's pretty. So it would be pretty surprising if an entire group of 8 people were able to quit smoking via.
Would that be like 1.6%, or are we gonna leave it at that?
I am always fine with you leaving probabilities as decimals. In fact, it's my recommendation that you do. I'm saying this as someone who just graded AP tests where there were students who transposed where the decimal point was and it caused them problems. You guys see what I'm saying? Like, there's no, if I don't care, pick the one that doesn't add a potential error to your thinking. Does that make sense? All right. All right, marbles selected from a bag containing 4 red, 5 green, and 6 blue marbles. You guys, how many total marbles is that? 15. All right, so we got 15 total. Cool. All right, so if the marbles are replaced after each pick, what is the probability of getting 3 green to be selected in a row? Okay. What's the so what would need to have, how can we describe in words what that event would mean? It would mean first one's green, second one's green, third one's green. Not 1/15 cubed. What's the probability that the first one is green? 5 out of 15. And if I replace it each time, what's the probability that the second one is green? Third one would be?
You just simplify it to a third.
Yeah, absolutely. So we could call this 1/3 to the third, if you really wanted to. 1/27. Which should be like 0.048, 0.047, something like that. Am I right? Okay, shush. I was thinking 120. I was trying to approximate it from 1 out of 25, but I was treating 125th as 1/20th. Right? Pathetic. Pathetic. All right, you guys, would this change if we weren't replacing the marble each time? Yeah, what would happen? We would have, the first one would still be 5 out of 15. Then 4 out of, then 3 out of 13. And then this is past Miss Meister's capabilities. The top number is 60. The bottom number is 210 times 13. 21 times 13 is, well, 20 times 13 is 260. I was getting there. And what is 60 out of 2730? Is anybody shocked to see that this probability decreased when we weren't replacing? No. And if we wanted to explain that in words, why aren't you shocked? It's not that it's just that the overall probability of green has gone down each time. Yeah? Okay. 2 events are independent if an independent event happens when the first event does not change the probability of the second event. You guys, which of these was independent? The top one, because if you drew out a green the first time, that didn't change the probability of drawing a green the second time. Dependent is the first event occurring changes the probability of the second. You get, and a way to think about this, let's answer, I'm going to ask you this question ever so slightly, okay? Not paying attention to what happened first. What is the probability that the second marble was green? But that 4 out of 14 relied on us knowing that the first one was green. But if we didn't know what the first marble is, do we know the probability of the second?
No.
No. Okay, that these two probabilities are what we call conditional probabilities. They are what happens given what has already happened, and you can't calculate it with, if you can't calculate it without knowing what's happened beforehand, that is a conditional probability. Is everybody good?
Yes.
Okay. All right, so let's do an example real quick. You draw 3 cards from a standard deck without replacement. What's the probability all the 3 cards will be a heart? Let's see. The first one, 13 out of 52 times. Without replacement becomes 12 out of times out of 50. Perfect. And then you smart people can figure this out. I'm not very good with numbers. Savina's like, you don't even believe me. What are we getting?
13, 52, 52. Is that you saying?
Huh?
On top is one, oh,
Go ahead.
1,716 over 132,600.
0.0126.
32,000.
Wait, I'm getting confused now.
0.0126.
132,000 plus 600. Okay, think of how to
Like
say
that?
it. Yes.
Which works out to be 0.216. Is that what you said?
No. She
Yeah,
got it wrong.
0.0119.
How did I do it wrong? Oh, I did do it wrong.
All right. You must randomly select 5 people from your department of 13 men and 16 women. What is the probability that you will select all women? What are your thoughts? 16 out of 29 for the first person, right?
Descending.
15 out of 29. 15 out of 28. Yeah, because you've got one less person. 14 out of 27, 13 out of 26, 12 out of 25. If you just want to go straight to the decimal, that would be fine. If you want to give me the fraction, I don't care. 0.0367. And you guys, this was the probability of all women, yes? What if I asked you what is the probability that you have at least one person who's a male? How would that, what does that look like? Computationally, this will be the easiest one I ask you to do today. You guys, what is the only circumstance in which you don't have at least one male on the committee? The only circumstance where you don't have at least one is that it's all women. Yeah, not well, one, but 1 because it's in the decimal form, but yeah, you have the right idea. Yeah. So to calculate the probability of at least one man, we could do 1 minus the probability of all women. Does this make sense to you guys? This concept that, and it's specifically at least 1 is the opposite of 0. The probability of 0, we can just do this. Yeah? So I want you guys to tie that the probability of at least 1 is equivalent to 1 minus the probability of 0. Cool? So you know. If someone wants to double check my arithmetic there, I think it's correct, but you know. I'm not always good with numbers. Why don't you guys do the next example? So did you guys do for the first part 0.4 to the 5th power? Or 0.4 times 0.4 times 0.4 times 0.4? So this is where yeah. Okay. And I don't know what 0.4 to the 5th power is. Can somebody help me out? Perfect. Cool? Are we all good for that one? So that answers the first question, that none of them. So what is the probability of at least one of them? I do want to point out to you, are you guys seeing the way I am labeling which one's which and all that kind of stuff, that I'm using this like probability notation of P and then what I'm finding that probability of? That is an expectation that you guys do that. Because if you just write down random decimals on your page, that doesn't communicate clearly to me that you know what you're finding. Okay? Cool? All right. Let's talk about conditional probabilities and even more. Okay, you guys, I'm going to draw a card from a deck. I'm telling you it's a heart. What is the probability it's a king? So 13 out of 52. Oh, I see. Yeah. Yeah, that's a no. Do we know that it's a heart?
Yes.
Yeah. So we don't need to worry about the probability that it's a heart. So it's just 1 out of 13. And so if I'm given that the card is a heart, are you with me that really what I want to do is the number of kings over the number of hearts? The minute I know it's a heart, my bottom number should be the number of hearts, yeah? Okay? Now, what if I said, what is the probability it is a king and a heart? Totally fine. You would multiply those probabilities. Everybody good? All right. So, here's a table of incidences of people driving. So this is one of those two-way tables, right? The two variables are, were they on their cell phone or not? The other variable was, were they in a car accident or not? Everybody good? All right. And right now, this two-way table isn't as helpful as I would like. So I'm going to real quick add how many of each category we have. Because that can be really helpful. So find the probability of getting into a car accident given that you are on a cell phone. So you said if you're given that you're on a cell phone, you're given that you are in this category, yes? Do you guys see what I'm saying? Yeah. It's just 3 over 21. And then, guys, you're going to see me write this. I'll be very flexible how you guys do this. But this is essentially saying what is the probability of an accident. So I'm going to let accident be here, and I'm going to call this cell phone, yeah? Okay? Given. So this is accident. This vertical line here means given. I'm going to use that all the time. If you are using just descriptive language, that will be fine for me. Know that when I use it, I'm doing that, okay? Okay. What are you thinking here? But we want to kind of want to look at them as two separate categories. Yeah? Go ahead, Shane.
So for calculating the male and female separately, so you can just do 17 plus 10 and then 17 divided by that.
Okay, so are you guys with me that of the male runners, there are a total of 27, and of the female runners, a total of 12? Yeah? All right, so the probability of a marathon given, again, I like to use that vertical line just because that's a very standard notation. It makes it easier for me to kind of keep everything straight. Given that somebody is a male is 17 out of 27. And given the probability of running a marathon, given that someone is a female is 8 out of 12. Now, does this answer the question of which one is more likely? Because now, if these were both out of the same number, we could directly compare them. But because they're out of, we got to turn them into relative things. I happen to know that 8/12 is 2/3, so I'm going to call it 0.667. Can somebody help me out with 17 out of 27?
0.62 or 0.63.
0.62 what?
69.
And then would that 9 round up?
Yeah.
So it's 0.630. Great. So who's more likely to run a marathon? Females. A lot more likely? No. Nah. And if we took a different sample of people, of runners, we might get different answers, yeah. That's unit 6 in terms of where we go with that. But. All right. We feeling okay? Okay. At this point,